Let's begin with section 1, which is measurement and their errors. So first of all, we've got fundamental and our derived units. So our fundamental units for the SI system are meter for length, the kilogram for mass, the second for time, and of course the ampere for electric current. We've then also got the Kelvin for temperature. We've got the mole for the amount of a substance, the candela for luminous intensity. So we've then got our derived units, such as the Newton for force and Joule for energy. Now they can all be converted into fundamental units. For example, the Newton can be converted into fundamental units via Newton's second law, as you'll be timesing mass by acceleration, which will give you kilogram meters per second squared. And this brings us on to uncertainty and error. So types of errors, you've got systematic error. These errors cause a consistent bias in measurement, either too high or too low. They arise from faulty equipment or flawed experimental design. So systematic errors can often be identified and corrected by calibration or by comparing measurements with their known standards. We've then got random errors. So these errors cause measurements to fluctuate around the true value. They are due to unpredictable variations in the measurement process. Random errors can be reduced by taking multiple readings and calculating the average. So accuracy and precision. Accuracy refers to how close a measurement is to the true value, while precision refers to the repeatability of measurements. High precision does not necessarily mean high accuracy. Uncertainty calculation. Absolute and relative uncertainty. Absolute uncertainty is the error for the margin of error in a measurement expressed in the same units as the measurement. For example, if we're measuring a length and our ruler has a resolution of 2 centimeters, our absolute uncertainty will be plus or minus 2 centimeters. On the other hand, when we are measuring a reading, we will use half of the resolution for our uncertainty. The reason we double half the uncertainty, or half the resolution, so we end up with the plus or minus resolution for measurements, is because of the fact that we're taking two readings. We're taking one at the 0 point, and we're taking one from wherever we want to measure, and that's the reason why we have double the uncertainty for a measurement as we do for a reading. You've then also got analog instruments, say for example an analog ammeter. This will have the same uncertainty as a measurement, for example, because you are measuring it from the starting point, whereas if you're taking a reading, then you can assume that the zero, say on a digital voltmeter, you can assume that the zero has no uncertainty. So combining uncertainties, when adding or subtracting uncertainties, their absolute uncertainties are added. However, when multiplying or dividing, their relative uncertainties are added. For example, if we have two lengths with uncertainties of 3 and 4%, you will add those values to get 7% when you multiply both of the values. We've then got ourselves particles and radiation. So we've got particle classification. We've got hadrons and leptons. Hadrons are particles made up of quarks bound together by the strong nuclear force. Protons and neutrons are an example of hadrons. Hadrons are further classified into baryons, which have 3 quarks, and mesons, which have a quark and an antiquark. So we've got leptons, which are fundamental particles that do not experience the strong nuclear force. Examples include electrons, muons, and neutrinos. Leptons are crucial in various processes, such as beta decay. We've got quarks and antiquarks. Quarks are the building blocks of hadrons. They are 6 types, or flavours, of quarks: the up, the down, the charm, the strange, the top, the bottom. Now, in this course, we only need to know the up, the down, and the strange. So quarks never exist alone, but always in combinations. Antiquarks are the antimatter counterparts of quarks with the opposite charges, but the same mass, of course. Antiparticles and annihilation. Antiparticles, every particle has a corresponding antiparticle with the same mass but opposite charge. For example, the positron is the antiparticle of the electron. Annihilation. When a particle and its antiparticle meet, they annihilate each other, converting their mass into energy in the form of photons. This process is described by Einstein's famous equation E equals mc squared. Fundamental forces. There are 4 fundamental forces. The gravitational force, which acts between all masses, but it is the weakest of the 4 forces. And the exchange particle for the gravitational force is the gluon. We then have the electromagnetic force, which acts between charged particles, responsible for electricity and magnetism. And the exchange particle for the electromagnetic force is, of course, the virtual photon. We've then got the strong nuclear force, which holds quarks together in protons and neutrons. And protons and neutrons hold together in the nuclei. So the exchange particle for that one is going to be the pion. Then the weak nuclear force, which is responsible for beta decay and neutrino interactions. We then have the W- and W+ boson for the exchange particle there. Radioactivity, types of radiation. Alpha radiation consists of a helium nuclei, which is 4-2, which are heavy and highly ionizing, but have low penetration power. Then got beta radiation, which consists of beta- electrons or beta+ positrons, which are lighter and more penetrating than alpha particles, however less ionizing for beta particles. Gamma radiation consists of high energy photons, which are highly penetrating but less ionizing. That's gamma radiation. We've then got ourselves nuclear decay equations. So in alpha decay, our nucleon number will decrease by 4 and our proton number will decrease by 2. And we'll end up with a helium nucleus emitted on the right side of our equation. We've then got beta- decay, which is where a neutron turns into a proton. Or in the form of quarks, for beta- decay, if it's a neutron turning into a proton, we will have up, down, down into up, up, down, so that'll be a down into an up quark. So our proton number will be increasing by 1, and we will also have a beta- particle emitted with a electron antineutrino. Then for beta+ decay, we've got a proton number decreasing by 1, as we have a proton turning into a neutron. We also have a beta+ particle emitted, which is just a positron, and a regular electron neutrino. Now in beta+ decay, we've got a proton turning into a neutron, so that would mean that we've got an up quark turning into a down quark. Next up, we've got waves. So wave properties, we've got transverse and longitudinal waves. Transverse waves have oscillations that oscillate perpendicular to the direction of wave travel, such as light waves and waves on a string. We've then got longitudinal waves, which have oscillations parallel to the direction of wave travel, such as sound waves in air. We've then got ourselves a wave equation, which is c equals f lambda, or v equals f lambda, where v or c is the wave velocity, f is the frequency, and lambda is the wavelength. This equation describes the relationship between these 3 properties for any wave or photon. Superposition or interference. So superposition principle, when 2 or more waves meet, the displacements add together. This can result in constructive interference, which is where the amplitudes add together, or destructive interference, which reduces the amplitude. We've then got interference patterns. We've got constructive interference occurs when waves are in phase, leading to increased amplitude. We've then got destructive interference, which occurs when waves are out of phase, leading to reduced or zero amplitude. We've then got diffraction and polarization. Diffraction is the bending of waves around obstacles and through gaps. The extent of diffraction depends on the wavelength relative to the size of the gap or obstacle. We've then got polarization, which is the orientation of oscillations in a transverse wave. Light can be polarized using polarizing filters, which only allow which only allows the waves oscillating in a specific direction to pass through. All other directions are absorbed. Standing waves. So a formation of standing waves are formed by the superposition of two waves travelling in opposite directions with the same frequency. This creates points of no displacement, which is nodes, and points of maximum displacement, which is antinodes. So harmonics and resonance. Standing waves on a string or in a pipe form specific patterns called harmonics, which depend on the boundary conditions and the length of the medium. Mechanics and materials. So let's begin with kinematics. We have our equations of motion, such as S equals ut plus half at squared, v equals u plus at, v squared equals u squared plus 2as. These equations relate displacement, initial velocity, final velocity, acceleration, and time, or SUVAT. Graphs of motion. Displacement time, velocity time, acceleration time graphs provide visual representations of an object's motion. We've then got dynamics, which is force. So we've got Newton's first law, which is what an object remains at in uniform motion unless acted upon by a resultant force. In other words, velocity is constant unless we have an external force acting upon the object. We then got Newton's second law, which is F equals ma, or the acceleration of an object is directly proportional to resultant force acting on it, and inversely proportional to its mass. So we've then got third law, Newton's third law, which is if body A exerts a force on body B, then body B will exert an equal and opposite force on body A. Or the standard definition, which is for every action, there is an equal and opposite reaction. As long as the objects are the same. Free body diagrams showing all the forces acting on an object, helping to analyse the resultant force and predict motion. Momentum and collisions. Momentum, the product of an object's mass and velocity, which is in the form P equals mv. And of course, momentum is conserved in an isolated system. So the types of collisions we have is the elastic collision, which is where kinetic energy and momentum are both conserved, whereas inelastic is where momentum is conserved but kinetic energy is lost. We've then got impulse. Now, change in momentum is equal to impulse, which is equal to the force applied multiplied by the time, which is force times delta t. Now, of course, force times delta t is therefore equal to change in mass times velocity, or mass delta v. So you can equate those together. Work done. Work done is done when a force causes a displacement, which is work done equals Fs cos theta. And obviously in a case where cos is 0, then theta is 0, and that force is acting along the parallel to the motion, then cos theta is just going to equal 1. So that just goes, but it's definitely important to note that the cos theta is there in case we have a force acting at an angle to the motion. Kinetic and potential energy. Kinetic energy is Ek equals a half mv squared. GP, or gravitational potential energy, is equal to mgh, which is mass times gravitational field strength times height. Power equals work done over time, or force times velocity. That's power, which has the units joules per second, or watts. Now, of course, you can use the fundamental units. Watts is not a fundamental unit, so you need to convert it. Materials, stress and strain. We've got sigma equals F of A, or stress equals F of A, which is force per unit area. Strain, E, is equal to the extension per unit length. In other words, delta L over L, which is the change in length over the original length. So the Young's modulus, then, is the stress divided by the strain, or the force per area divided by the extension per unit length. We then have elastic and plastic deformation. So elastic deformation is reversible. It's where the material will return to its original shape, whereas plastic deformation is irreversible. The material is permanently deformed. This brings on to electricity. We've got electric current and charge. Current is I, which is the rate of flow of electric charge. I equals Q over T, measured in amperes. Charge, Q, is the amount of electric charge, measured in coulombs. 1 coulomb is the charge transported by a current of 1 ampere in 1 second. Potential difference in resistance, potential difference voltage, the energy transfer per unit charge, V equals W over Q, or E over Q, is measured in volts. Ohm's law, the relationship between voltage, current and resistance, or V equals IR, provided that the conditions are constant, such as temperature. Resistance, the opposition to the flow of current, measured in ohms. Series and parallel circuits. Series circuits, components are connected end to end. The current is the same through all the components, but the voltage is divided between them. Parallel circuits, components are connected across the same 2 points. The voltage is the same across all the components, or across all branches, but the current is divided between the components on each branch. Or the current is divided among each branch. So the current is not always going to be the same down each branch. Electric power and energy. Power is the rate at which electrical energy is transferred. P equals IV, measured in watts. Alternative formulas include P equals I squared R and P equals V squared over R. And of course you can derive those via V equals IR, but they are given to us in the formula booklet. E equals PT, which is energy transferred, which is power times time, where energy is E and joules is J, P is power in watts, and T is time in seconds. Now E equals P times T, because if power is energy per time, times it by time, you end up with energy. Kirchhoff laws. You've got Kirchhoff's first law, or Kirchhoff's first law, which is the current law. The total current entering a junction is equal to the total current leaving the junction. This is a consequence of the conservation of charge. Kirchhoff's second law, which is the voltage law. The sum of the electromotive forces, EMF, around any closed loop equals the sum of the potential difference or voltage drops around the loop. This is a consequence of conservation of energy. So basically, the sum of the voltages around a series circuit is equal to the total EMF supplied by the battery. Section 6, further mechanics of thermal physics. This will be just further mechanics in terms of circular motion, SHM, etc. So we've got centripetal force, which is F equals mv squared over r. There's also a few more equations for circular motion, such as A equals v squared over r, which is the acceleration of an object moving in a circle directed towards the centre. We've then got SHM, simple harmonic motion. Characteristics is when an object in SHM experiences a restoring force proportional to its displacement from the equilibrium position and directed towards that position. F equals minus kx, which is basically meaning that force is inversely proportional to the displacement, or acceleration is inversely proportional to the displacement. So, for example, we increase the force and we decrease the or we increase the acceleration and we decrease the displacement from the equilibrium position. Equations for SHM. We've got A equals minus omega squared x, where omega is the angular frequency or the angular speed, which is measured in radians per second. The displacement of an object in SHM can be described as x equals a cos, all in brackets, omega t plus phi, where a is the amplitude and phi is the phase constant. Now that's not usually used very much, but yeah, that's that. So that's all of the paper one covered pretty much. Linear motion circuits, potential dividers. Right, so potential dividers are essentially two or more resistors which we can essentially use to change the resistance across a component. So we can move the cable between a point in between the resistors or including both resistors. And obviously if we increase the resistance across a component, then we increase the voltage also. So that's important to note when we're using things such as LDRs and thermistors, and variable resistors as well, of course. We've then got resonance, which is where something oscillates at the same frequency as its natural frequency, which obviously the result of that is that we have the maximum possible amplitude. We've then got moments. Moments is force times the distance perpendicular to the pivot. So force equals the perpendicular distance from the pivot. We've then got equilibrium, which is where the resultant force is zero in a system. We've then got a bit of trigonometry in that as well. So just knowing how to resolve our forces into horizontal and vertical forces. We've done impulse, done density. Density is going to be the mass per volume, or m over v. Springs and Hooke's law. So Hooke's law is where we say that the force exerted on a spring is proportional to the extension up to the limit of proportionality. And then after that we will have our proportionality limit, and then we'll have our elastic limit, which is where we get basically plastic deformation. And then we've got this can link to Young's modulus as well, where we have our ultimate tensile stress, which is the point where we have our sort of point where the highest amount of stress can be exerted on a material without it breaking. And then we've got our breaking point, which is shortly after that. Stress strain, Young's modulus, we've done all that. Mechanical waves, done that. Polarization, done that. Single slit diffraction. Right, so single slit diffraction, we've got our main central maxima, which is in the middle, and then we've got our smaller central maxima to the sides. Obviously it's all going to be symmetrical, but each maxima after the first maxima is going to be a lot smaller in amplitude, and they're going to be half the width as well. So every one after that has half the width. The double slit, obviously we've got equal fringe spacing, equal brightness of maxima, and that's pretty much that really. They're all the same brightness for the maxima, all the same brightness for the minima, all the same distance apart, right? It's important to note as well that the diffraction pattern, we call it a diffraction pattern for single slit, but we'll call it an interference pattern for double slit. This is because the waves essentially diffract when it's passed through a single slit. Of course they do diffract as well when we go for a double slit, but the pattern that we see is not because of diffraction entirely. It's mainly because of interference of the two diffraction waves, the two diffractive waves really. So we need to know as well if we have white light. If we have a diffraction pattern for white light, we have a very wide central fringe which is surrounded by much dimmer rainbow fringes. Each rainbow fringe will go from blue to red as we move outwards from the centre. It's then important to note that red has a much greater wavelength than blue, as we have blue shift when something moves towards us, red shift when something moves away from us. We then have inclined planes, which is which is there's not really that much you need to know for that. As long as you can resolve forces, and use Newton's laws that I've discussed, you'll be fine with that. You've got ionization, so you've got excitation, which is when something, an electron, will receive energy, which will cause it to excite into a higher energy level. Then this electron will always de-excite back down to a lower state, or the ground state, and it will release the energy difference in the form of a photon. Now this photon will have the exact energy of the energy difference between the two energy states, which will cause, as a result, a wavelength for that photon of an exact wavelength because of the energy. So that's why we say that when we've got different de-excitation paths, it can go straight from the top to the bottom, or it can step down one by one. We will end up with a variety of wavelengths as a result. So if we get a question saying how many wavelengths could we possibly get, you need to go through each path and calculate the amount of paths down we could possibly have and the amount of energy differences that we could have. We've got antiparticles, we've done that. Bosons, done that. Exchange particles, done that. Specific charge. Specific charge is going to be the charge of the charge of anything divided by its mass. So you've got the charge in coulombs, you've got the mass in kilograms. So for example, the charge of an electron is going to be 1.6 times 10 to the minus 19. The mass you want then divide by the mass of electron, which is I don't know what it is. It's like 9.11 times 10 to the minus 31 or something like that. We've then got the de Broglie wavelength. So the de Broglie wavelength tells us the wavelength of anything with mass. So to calculate the de Broglie wavelength, we use the Planck's constant and divide it by the mass times the velocity. That's all we need to know for that. So essentially anything with a mass and a velocity has a wavelength. So the smaller the mass, the more substantial the wavelength is, and leading to diffraction if we've got a big enough wavelength. Single slit diffraction, done that. Positioning waves, done that. Polarization. Material properties, work, power and efficiency, moment, simple pulleys, dynamic systems, centripetal force, circular motion. Yeah, it's important to note for circular motion as well that the resultant force is directed towards the centre. And if we've got, for example, a car moving in a circular path, we're going to have a reaction force from the wall of the thing that it's driving on. Say it's going in a circular loop. The loop will be exerting a reaction force directed towards the centre, and we will also have mg. So when we're at the bottom, our centripetal force is going to be at the lowest, but then when it's at the highest, our centripetal force is going to be at the highest, because we've got reaction force and mg acting towards the centre. We've then also got vectors. Nothing too bad there. Standard index form. We've got quantities and units. So you've got femto, pico, nano, micro, milli. You've then got kilo, mega, giga, tera, peta. Right. And I think that's all we need to know for those. Off the top of my head. Then got EMF. The EMF equation is going to be EMF is equal to the I, which is current, multiplied by R plus R, which is the resistance in the circuit add the internal resistance of the cell. That's if we have a real battery supply or a real cell with internal resistance. So we also have real ammeters and real voltmeters. So the ideal ammeter is going to have a resistance of 0, obviously, because if we've got more resistance, then we're going to have a lower current. But then in a voltmeter, we want no current running through it. So we want essentially infinite resistance going through a voltmeter. But in reality, they don't have infinite resistance. They're going to have less than infinite resistance. And as a result, it's going to reduce the potential difference across the component. Then we've got our conservation laws, superconductors. So essentially when something reaches a certain temperature, which is called the critical temperature, we will have no resistance across that material. We've then got variables. So you've got the independent variable is so the dependent variable is the thing that is dependent on the change. So the dependent variable is the thing we measure, and the independent variable is the thing that we change. We've then got logarithms and exponentials. Logarithms is essentially the most common use for logarithms is trying to get a equation into a linear form. So usually we'll log both sides. For example, y equals ae k to the x. We'll log both sides and we'll get log y equals log a plus log e to the minus kx. And then we'll end up with log y equals kx plus log of a. Because when we log something, or when we learn something that's e, we just end up with the exponent of the power, the index, whatever you want to call it. So yeah, that's pretty much everything covered now. I guess you've got total internal reflection. That's the last thing. We'll end it on that. So total internal reflection is when something passes a boundary into a lower refractive index, we can get total internal reflection, which is where none of the light or none of the wave is refracted or passed through. All of it's reflected at the same angle of incidence that was incident on it. So provided that the greater the ratio between N1 and N2, which is the refractive index of both of the substances, the greater the ratio, the greater the ratio, the smaller the angle we need. So if our angle of incidence is greater than the critical angle, which is sine to the minus 1 or arc sine of N2 over N1, if our angle of incidence is greater than that critical angle, then we will have total internal reflection. But if it's less than, we won't have total internal reflection. Instead we'll have some reflection and we'll have some refraction. Just depends. But yeah. We then have a little bit more on that, and it's total internal reflection in optical wires. So we've got the core, which is where the actual rays will bounce around at, and then you've got the cladding, which is the thing around the core, which has the lower refractive index. So the core will have a higher refractive index. We've then got pulse absorption, which is basically when we'll have pulse absorption, which is where the amplitude or intensity of the wave decreases. So pulse absorption can make it difficult to decode the signal at the other end. Pulse broadening as well, which is where the amplitude will decrease, but then the time period for the actual ray to be inbound is a lot bigger, and it's not square shaped anymore either. It can be a bit like a trapezium. So to reduce that, we'll use repeaters, which are quite useful for that kind of thing. We've then also got using something called a we can have a really thin core, which will essentially limit the amount of angles. Yeah, so it's called a monomode fiber, and it essentially removes or kind of prevents multipath dispersion. We've also got the fact that we can decrease the ratio between the cladding and the core. Now what this will do is it will reduce the amount of different angles going through it, so we'll have a much lower range of angles, which, because we've got a much lower range of critical angles, or angles where we'll have TAR, and that's that really. That's everything you need to know on that really. You've got your graphs as well, but I can't really go through the graphs because you have to draw that out and work out the area. So just work through your equations really as well. So look at your equation, look at your axes, look at what the question's asking. If it's asking us, for example, what's the displacement of the graph, and it's a force time graph, you're going to find the area under the graph. And it's just the fact that you should just be able to pull off the graph straight away, calculating gradients. If you've got a curve graph, draw a tangent and then work out the gradient of that part. Also, if you need to work out the area under the graph, but it is a curve graph, just either count the squares or just make some trapeziums, draw some shapes, draw some triangles, squares, whatever. If it isn't curved and you want to work out the area under the graph, much simpler. Just make some shapes under the graph. Draw some triangles, draw some squares, draw some rectangles, draw some more triangles, draw some trapeziums, do whatever you want. And that's pretty much just that, really. Yeah, you've got wave particle duality as well. So photoelectric effect is when we have photons incident on a metal surface, and what this metal surface will then do is we will excite electrons from the surface of the metal, and they'll then be emitted from the surface of the metal. And this is evidence actually of the particle-like nature of the photon. And it's important to note that the frequency through E equals HF increases the energy of the particle-like photon, which will then mean that we'll have a higher energy photon, which means we can emit a electron with a high work function, because of course through our work function equation with kinetic energy, energy of a photon and the energy required to emit or excite an electron from the surface of the metal. We've then got wave-like nature of light or photons, which is going to be diffraction, interference, quite a few things you could say there. You've then got the fluorescent bulb. So the fluorescent bulb experiment is where we have a gas of, say, hydrogen, and we put a gas chamber of hydrogen in a circuit, and as electrons flow through this chamber, they will collide with the ions of hydrogen in the in this sort of thing that we've got attached to it with the hydrogen gas in, and as a result we will excite the electrons from the ions of hydrogen or whatever gas we're using, and then after that the electrons inside of this hydrogen core will de-excite, and as a result of the de-excitation, as I've previously discussed, we'll get photons emitted. And the fact that we've got photons emitted from that discusses the fact that their wave-like nature as well, because we can get interference then from a diffraction pattern. So what we can do is we can have this hydrogen tube, and then next to that have a diffraction grating, and then have a screen, and we can then see the diffraction pattern along that screen. Just check if I've missed anything out on that there. No, so the electron's particle-like behaviour is light. So the excitation of atoms in the fluorescent screen is particle-like nature, but then you've got the photoelectric effects for particle-like nature as well. You've got light having a wave-like nature through Young's double slit, and light having a particle-like nature for photoelectric effects, whereas electrons, through electron diffraction, have wave-like behaviour, but then through particle-like behaviour, as I just discussed with the collisions of the electrons on the ions electrons in hydrogen, that's obviously discussing it as a particle-like form, isn't it? So that's going to be evidence for a particle-like behaviour for electrons. We've then got a diffraction pattern on the fluorescent screen from electrons. You've got bright and dark fringes for an electron interference pattern. That's basically all of that, really. Significant figures. Just make sure you give your answers in the form of significant figures that are in the question. Or if it's asked you to give the answer to a certain amount of significant figures, obviously do that. But even if it's just a 0.0 on the end, just keep it to the same, or the smallest amount of significant figures that you've been given in the question. It's usually a safe bet. Yeah, so I think I've covered everything on there really now. Yeah, just quickly going through all that. Yeah, that's fine. Alright, thank you very much for watching or listening.